All right, so to help us start to think about what Euler's number is, there's actually a special formula that you can see here listed in this table. And what we're going to do is see what happens when we plug in different values for the variable, in this case different values for n, into that formula. And so let's start to take a look at a couple of these together. So for example here, when n is equal to 1, I'm just going to write this off to the side. It's going to be 1 plus 1 over 1 raised up to the power of 1. So really the two positions where we have the n, where we're plugging the number in, are the two places there that are highlighted. And so what we end up with here are a lot of 1s, but if you think about how we would actually simplify it, in our parentheses, 1 plus 1 is 2, and then we've got 2 to the first power, so that output would be 2. All right, well, let's think about what this would be for the second input. So if we put 2 into this, we get 1 plus 1 half, which is really 1 and a half. You can think of it as 1.5, and then we are squaring that. So if we were to go to our calculator here and do 1.5 squared, we end up with 2.25. Thank you. Can you put that away? Can you put your phone away, please? All right, so we could continue in that same way, plugging the values in one at a time, checking to see what we get for the output. But I want to actually show you up here on my calculator screen a shorter way to fill in the rest of our table. So you could actually just follow along with my calculator here. I'll keep everything displayed for you. So what I'm going to do is go into the y equals, and I'm going to type in the formula. So it's going to turn into x instead of n, but it will essentially be the same thing. So in parentheses here, 1 plus 1 divided by x. I'm going to close the parentheses and raise it up to x. We've got our formula typed in. Now, our calculator has a feature where we can access a table where you can tell your calculator like what numbers you want to input into your function, and it'll do all of the work for you and tell you what is the corresponding output. So before we go to that table, I'm going to go to Table Setup by pressing Second Window, and there's a feature down here where it says Independent. The independent variable is like the input variable, the x, and instead of auto, I'm going to change it to at. And so that's just a nice feature because what we're going to see here in just a moment is a totally blank table. We're going to get to type in what values we want to plug in for x. So to get to the table, we're going to get there by pressing Second Graph. All right, now let's check the 2 that we already calculated by hand. So when we plugged in 1 for the variable, so if I type in a 1, first it's going to show up down here at the bottom of my screen. If I press Enter, it's going to put it into the table. And notice how we get the exact same output of 2. And then if we plug 2 in, we get the same answer of 2.25. I'm going to go ahead and continue typing these in all the way up through 10. And what we'll do here on our paper is just copy down the decimal value that we see. So now we're going to see, well, what would happen if we drastically increase the number that we're inputting in. So we're going to finish up by plugging in 100, 500, 1,000. We're going to go all the way up to 1 million. We're going to see what happens to that output. So I'm going to actually clear this table here really quick so it'll be easier for us to see if we have that blank table position to start with. And we'll go ahead and plug in those final 4 numbers. So notice how that when we inputted 100, we made a little jump. So we got out of the 2.5 range, and this is now at about 2.7. If we plug in 500, it is still hovering around 2.7. It's just a tiny bit more. Now we're at 2.7156. Well, if we input 1,000, teeny tiny bit different, we're up to 2.7169. And when we do 1 million, so that's going to be a 1 followed by 6 zeros. All right, when we input 1 million, it doesn't really change very much at all. It's still about 2.71. The decimal digits after that changed just a little bit, and it got up to 2.7183. So what we're seeing here is that as that number that we plugged in got bigger and bigger, that output is kind of staying right about at the same number. Like, you can think of it like on a graph, it would be like kind of flattening out at the value of 2.7183. If we were to continue to plug in bigger and bigger numbers, our output would actually get us more accurate and closer to a special number called E. And that little lowercase e there is the symbol that we give to Euler's number. So Euler's number comes from inputting larger and larger values into that formula that we saw in our table. So he discovered this. And so if you take a look here in the box, there are actually a lot of decimal digits after the 2.7183, which is like what our calculator rounded it to. This is actually going to go on and on forever. It's actually a never-ending, non-repeating decimal. So we can see Euler's number there in the box. A characteristic of this number is we call it an irrational number. And that means a couple of things. The first thing is that it cannot be written as a fraction. And it is a never-ending, non-repeating decimal. A number that we could compare this to is kind of like the number pi. Okay, it must be really windy outside. When it gets super windy, the projector just shakes like this, so I hope that's not too distracting. Okay, so suppose that we had an exponential function that has e as the base. So e is just a regular number. Like, at any time we see e or we write e, I just want you to think like, oh, it's like 2.7183. Like, that's the value of e. And so if we had an exponential function with that as the base, bless you, it would be y equals e to the x. And so the inverse of that would be y equals log base e of x. So kind of the big thing that we've seen throughout this whole unit is that the exponential and log that have the same base are inverses in one another. So it's no different from when we had 2 to the x was the inverse of log base 2 of x. We're just using a new base here. We're just using base e. And so there's actually a special way that we are going to write out log base e. Instead of writing it with log, we're changing it all together, and we're going to write it with ln. So when you see ln, it is called a natural logarithm, or natural log, and it really just means log base e. So it's kind of like another situation where it's a log where the little base number is not shown, but we don't want to get it confused with it being base 10, and so instead of using log, we changed it altogether to be ln. So we're going to really just continue today doing various things with base e or ln. And so we're going to start by doing some evaluating. So we're going to evaluate the logs listed here. And so when we think about this first one, ln e, what this is really asking is, what is log base e of e? And early on, when we very first start working with ln, it might be helpful for us to write this out. Log base e can connect it back to what we did with the other notation for regular logs. And so here's the question this is asking. E raised up to what power equals E? It would be 1. Yes. Anything raised up to the first power equals itself, and so ln E equals 1. All right, let's think about the next one here. So ln of E squared. If it helps, again, to think about a little base E, you could draw it in there to remind you of that. So this is asking E raised up to what power is E squared? Yeah, go ahead, Daniel. 2. Yeah, E to the second power equals E to the second power. Seems a little bit redundant. How about the next one here? So this is ln of square root E. So this is asking E raised up to something equals square root E. There's a special exponent that makes it turn into a square root. It's 1/2, that's right. So let's make a little reminder of this off to the side here. Anything raised up to the 1/2 is equal to a square root. Okay, actually, I want to add in 1 or 2 more here, since we have a little bit of space off to the side. So I'm going to add in a part B, and have us think about how we would do ln of 1 over E. So if we want to turn this into a fraction, we have to raise it up to a negative exponent. So this one is equal to -1 because E to the power of -1 is the same thing as 1 over E to the positive 1. So I just want to put in a little reminder there about dealing with a negative exponent. And so if we were to look at one more, kind of like that, let's make it something like ln of 1 over E to the 5th. What do you think that exponent, or that answer would be? It's going to have something to do with 5. Yep, and we're going to make it negative because we see that it is written here as a fraction. So E to the -5, we write that off to the side, is really the same thing as 1 over E to the positive 5. So that's a helpful thing to know and remember what you do if your exponent's negative. All right, so that's a little bit of evaluating natural logs, so thinking about log-based E. Okay, we are going to go ahead and turn over to the back side. Box. All right, so first thing, we're just going to summarize a few things that we've talked about so far with natural logs. So we saw the way that a natural log is written. It's written as ln, but it really means the same thing as log base E. Just kind of a shorter, faster, nicer way to write that. And that function there, y equals ln x, is the inverse of y equals e to the x. All right, and then we also saw that E is just the number, it's about 2.7183. It's just a number kind of like pi. So we would say pi is about 3.14. E is about 2.7183. All right, now what's nice about what we're looking at today is a lot of the things that we have been doing are all going to work exactly the same way with an ln or thinking about having a base of E. So if we think about the properties to rewrite expressions, before we use properties to condense and expand expressions, it works exactly the same way with ln. So if you have ln of something plus the ln of something else, we can combine them together by taking the ln of their product, meaning we're going to multiply together the two pieces, in this case, multiplying together the m and the n. So when we see addition, this is the one where it turns into multiplication. All right, and then we also have our property involving subtraction. And we saw that when they are being subtracted, whoops, that was not intentional. We need to keep it as ln the whole time. I accidentally wrote log. ln of m minus the ln of n, altogether it's the ln of m divided by n. All right, and then our last property helps us to deal with, I almost did it again. It helps us to deal with taking the log of something that's holding up an exponent. So the ln of m to the n, we're just going to do the same thing. We're going to take that exponent of n, and we're going to move it to the front, so it's going to multiply by ln m. The properties are really just the same as before. And then the last thing, we're going to write in a few pieces for strategies for solving equations. Solving equations, that's really been our main focus for the week. We are going to just have some slight variations to that with base E today. So our main thing to solve equations is that a natural log, which is ln, undoes an exponential with base E. Okay, so here are two situations that could happen where we could use them. So let's say that we are solving an equation, and we have an e to the x, and so our x is in the position of an exponent. We want to get that x out of the exponent and down onto the ground. So because this is an exponential part with the e as the base, the way that we're going to undo that is by taking the ln. Now, normally with an equation, if we had an equal sign, we would take the ln of both sides. But on whatever side that the variable is at, that ln is going to cancel out. It'll undo the base of e, and the little exponent part, the x, is just going to come down to the ground and just be a regular x. So that's how we can use this if we are solving an exponential equation. So this is like what we did on Tuesday in our 7.5 Part 1 lesson. The other scenario is that we might have an equation that involves an ln of x right from the start, and we want to try to undo the ln. We want to get rid of that. We want to be able to get the x out. And so this is where we're going to apply a base of e. The e is going to hold up the ln x. The ln x is now going to be in the position of an exponent. So if we have e raised up to that as a power, it's going to undo that ln that's in the exponent, leaving us with just x, which accomplishes our goal of getting rid of the log and getting the little x part out of it. All right, so now we're just going to apply some of this, what we've talked about here with our properties and solving equations. We're going to finish up by looking at a few specific problems. So we're going to begin with our properties, doing some condensing and expanding. So this first one actually is wanting us to expand. So notice how we're using ln instead of log. And so when we're expanding, we always want to look for like what's happening first on the inside. Are they being multiplied or is it being divided? And so in this case, because they're being multiplied, we can go ahead and split this apart with addition. So we're just going to do the ln of the first part plus the ln of the second part. And then just as we've seen before with expanding, if you do have an exponent up here, we'll just go ahead and move that up to the front. So our final answer, we get 2 ln x plus ln y. All right, we're going to continue down below for the next one where we are condensing. So notice how this one also involves ln. It's a little bit longer. We're going to condense it, which means we're going to shorten it down. We want to write it as a single ln. We don't want to have ln listed twice. So we're kind of going in the opposite order as what we just did when we were expanding. And so notice that we do have some numbers out in front of each one. Well, our first step here is going to be to move those numbers back up to the position of an exponent. All right, and then we're looking at that subtraction sign to help us with the final part. So we're going to condense it down to a single ln. X cubed is on the numerator. We've got y to the 5th down on the denominator. Nothing else we need to do. That's our final answer, all the way condensed. All right, we're going to continue with the problem in the box directly below that one. So now we're going to start to look at solving equations. And in question 6 here, we didn't say anything about this at the top of our paper, but I want you to know we can do the same base method even if you're dealing with a base of e. And so remember from Tuesday, the main idea with the same base method is if you have the same base holding up exponents, then whatever's in the position of the exponents, they must be equal to each other. So I like to write this out like if b to the m is equal to b to the n, and that base of b is the same on both sides, then simply m must be equal to n. So the way we can tell if it's going to be possible for us to do this is that you notice that there is a base of e already on both the left side and the right side. We're just going to make one small adjustment on this right-hand side. So remember that 1 over e to the 5th is really e to the negative 5. So we don't want to do the same base method if we're dealing with a fraction of any sort. We just want it to be a regular base of e sitting on the ground on both sides, holding up something in the position of an exponent. So now that we've accomplished that, we've got our bases the same. We're just going to simply set our exponents equal. So if this first statement is true, well, then the exponents must equal. Then 2x must be equal to negative 5. And we'll just go ahead and divide both sides by 2. And the final answer we get here is negative 5 halves. Now, unlike the log equations that we were solving on block day, when you're solving exponential equations, you're never going to get an extraneous solution. Like, this is a negative answer, but that's okay, because if you were to plug it back in, you can have a negative exponent. That's fine. You can have a negative exponent, you can have a positive exponent, you can have an exponent of 0. There's no limit to what type of number you input into an exponential equation. So I thought that would be worth mentioning, since the last time we talked about how sometimes negative answers are extraneous, That's only when you're solving a log equation, because you can't take the log of a negative number. Okay, sometimes we can't use the same base method, and so going back up here at the top, like on number 3, we're just going to use the ln both sides method. And so before we do that log of both sides here, let's go ahead and subtract 5 over. So we always want to think about isolating the exponential part, the base holding up the exponent. And remember on Tuesday, what we would have done here is we did a log on both sides, and we wanted the log to have the base matching this base that was holding up our exponent. So really what we would do here is log base e on both sides, and we learned that log base e is ln. That's what ln means. And whatever we do to one side, we just have to do the same thing on the other side. So we're just going to put an ln in front of both parts, what we previously had. And the magic happens here on this left-hand side. That ln is going to cancel out that base of e. So here we just have 4x equals ln 10. The final step we need to do to get x by itself is just divide both sides by 4. Go ahead and grab your calculator out. If you have a calculator with you today, if you didn't already grab that, I want to show you how you can type the final step into our calculator. It's going to be super easy because just like we have a log base 10 key, you have an ln key. You might have seen that key before, maybe wondered what it was. If you didn't see it, that's okay. It's probably close to where your log key is. On my graphing calculator here, ln is right below the log key. So it's going to make it really easy to do like anything that's log-based keys. So because we had ln 10 divided by 4, I'm going to type that in like this. Make sure we close the parenthesis around the 10 before dividing by 4. So if we typed it in correctly, you should get about 0.58 would be our final answer here to this equation. Okay, so those were exponential equations. We're going to finish up. Our final 2 equations are both log equations. So this is like what we did on block day because we have a log already in the original equation statement. So because we know that ln is really log base e, to think about what's going to cancel out or what's going to get rid of that log, we're going to have to apply a base of e on both sides, holding up those sides like as exponents. So the original left side now becomes an exponent of e. On the right side it was just 4, so we have e raised up to the power of 4. We always have to do the same thing on both sides. Now on the left here, the e holding up the exponent part, that's going to undo. It'll cancel out the log. So that's going to go away, and then we just have 3x minus 1 equals e to the 4th. Now, before we type this one into our calculator, I'm going to show you how you can do that if you have an answer that involves e. But what I like to do here is get x by itself first. So let's just think about adding 1 to both sides and then dividing both sides by 3. So we just turn it into like one step, one thing that we're typing into our calculator. If you do it all in one piece, we do need to make sure that we have parentheses around the numerator parts on our calculator to keep those pieces together. And then it'll make sure that it gets an answer on the top and it divides the whole thing by 3. So let's jump back over here to our calculator screen. And the first thing I want to actually show you is where you can type in e. So kind of like how you have a pi symbol, you have a way to type pi in by pressing this. The E is right below that, so it should be labeled right on top of the divide sign. And so if you press second divide, and at least on the graphing calculator, you're going to see E come up on the screen. And if you actually just press enter here, I want to convince you that this is the same E that we talked about at the start of today. So notice how, yep, it's about 2.7183. All right, so let's do some parentheses to actually type in the result of our equation. So we're going to do parentheses around the numerator, E, and then I'm going to find my exponent key. So E raised up to the power of 4. Arrow over to the right to go ahead and add 1. And then close the parentheses and divide the whole thing by 3. Our final answer here should be about 18.53. All right, very last equation we have today is another log equation, since it involves ln right from the very start. But similar to some problems that we saw in the last lesson, sometimes we have to condense it first before we can do anything to cancel out the logs. So notice that these are being added, and so that 2x and the 3, those are going to multiply together. So it's going to be ln of 6x equals 2. All right, and then we'll do the same thing that we did in the previous problem. So we're going to do E raised up to the left side. We're going to do E raised up to the right side, which really just ends up being E squared. So it's going to cancel out the log. We've got 6x equals E squared. So x is E squared divided by 6. All right, so here's how we can put that in our calculator for our final step here. So E squared divided by 6, and we see that that answer is about 1.23.